Okay, so if we start all the way with hydrogen, okay? So I've got my hydrogen and I've got my 1s. Sometimes we put a box or sometimes I can just draw a line. So I can do hydrogen and then draw a line and there's my 1s, okay? So hydrogen has an atomic number of 1, which means it has 1 proton, okay? For a neutral hydrogen atom, that means we also have 1 electron. So I'm going to go ahead and put in 1 electron, all right? So there's an orbital diagram for hydrogen. And then my electron configuration is just 1s1, okay? All right, when we come over to helium, we've got 1s2, okay? So helium, again, normally we just draw a line, okay? So I have an atomic number of 2, which means for a neutral helium atom, I have 2 electrons. So that's my 1s. So I have 1, 2, okay? And so there's my configuration, 1s2. Okay, now that's the end, all right? I'm full. I can't fit any more in my s orbital, okay? So in energy level 1, we only have access to that single s orbital. So we're full. We can't do anything else, which is why now to go to lithium, we have to drop down to period 2. Okay, so there's lithium. Okay, lithium has an atomic number of 3, which means 3 protons. So a neutral lithium atom will have 3 electrons. So when I fill it, okay, because I'm in period 2, so I have access to those 2 p's. So when I fill it, I'm going to go 1, 2, I'm going to fill that up first, and then I go to my 2s, and there's where I get my 1s2, 2s1 for my lithium electron configuration. Okay, carbon, all right, is a little bit further over. Carbon has an atomic number of 6, which means for a neutral carbon atom, I need 6 electrons. So when I fill that, there's my 1s, there's my 2s, my 1, 2, 3, 2p. Okay, so I'm going to fill my 1s, so there's my 1, 2, okay, then 2s, 3, 4. And then now that I'm in p, remember, once we're in a specific sublevel, we have to put single electrons in before we spin pair. So that's why electrons 5 and 6 for carbon are by themselves there in that 2p set, okay? And that's where we get the 1s2, 2s2, 2p2, because I have 2 electrons in 1s, 2 electrons in 2s, and then 2 electrons in 2p. Okay? So let's take a look at the periodic table here. All right? What if I wanted to do, say, magnesium? Okay? Magnesium is in period 3. Okay? So to do magnesium, we're going to have 1s, 2s, 1, 2, 3, 2p, and 3s, and 1, 2, 3, 3p, okay? So that's what we have that we're going to fill in period 3. Okay? So magnesium has an atomic number of 12, so we have 12 electrons for a neutral magnesium atom. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So magnesium's electron configuration is 1s2, 2s2, 2p6, 3s2. Okay? Let's see here. What about, let's drop down to period 4 and let's look at scandium. Okay? So scandium has an atomic number of 21, and we're in period 4. So we have our 1s, we have our 2s, we have our 1, 2, 3, 2p, we have our 3s, our 1, 2, 3, 3p. Now we have our 4s and our 1, 2, 3, 4, 5, 3d, and then our 1, 2, 3, 4p. Okay? So we need 21 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, so it's a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Okay, so that is our configuration for scandium. Okay, so here's a few back to period 2. So there's lithium through neon. Okay, and then if you notice though, when we started doing some of those other configurations, they got really long. Like scandium over here, that got incredibly long. Okay, so what happens when we get really long configurations? Well, let's look at phosphorus here. Okay, phosphorus has an atomic number of 15. All right, so we have this configuration here of 1s2, 2s2, 2p6, 3s2, 3p3. Okay, now remember, when we fill an energy level, we now drop down to the next period and start the next energy level. So phosphorus is in period 3, which means everything that comes before the 3s was filled in period 2. Okay, well, what ends period 2? Neon ends period 2. So 1s2, 2s2, 2p6, that is neon's electron configuration. So I can do a shorthand version of my orbital diagrams and a shorthand version of my electron configurations as shown right here. I can put the previous noble gas in brackets because what I'm saying there is that I have all of the electrons that neon has. And then whatever I write after that, now that builds it up to where we are in the periodic table. So I have all the electrons that neon has plus a 3 plus a 3s2, 3p3. Okay? So let's go back and look at that scandium again. Okay? Scandium is in period 4. Okay? Which means that it's got all of the electrons that argon has, plus what we're going to build up in period 4. So I can do my shorthand or my noble gas configuration, and I can do argon in brackets, and then I get 4s2, 3d1, which makes it a lot easier to do. If I do the diagram, I can still put argon, and then I'll do my 4s, my 1, 2, 3, 4, 5, 3d, 1, 2, 3, 4p, because that's what gets added after argon. And so for scandium, I've got the 1, 2, 4s and the 1, 3d. Okay, so I can do that with lots of different configurations. So again, this is our shorthand or noble So we go through and we fill, as would be logical. Now, in period 3, or not period 3, sorry. In period 4, I'm looking at the wrong thing. In period 4, I have 2 exceptions to the rule, okay? So chromium and copper have unusual electron configurations. So chromium expected would be argon, and then again we've got our 4s, 1, 2, 3, 4, 5, 3d, and then 1, 2, 3, 4p. Okay, expected for chromium would be 2 4s electrons and 1, 2, 3, 4 3d electrons. All right, this is not what we see. This is actually not as stable. So chromium, the actual configuration is we still have our argon. Okay, there's our 4s, 1, 2, 3, 4, 5, 3d, 1, 2, 3, 4p. Okay, the actual is we get a single 4s and 1, 2, 3, 4, 5 3d electrons. So this is more stable. So chromium, we get argon, and then 4s1, 3d5. Okay? We see something similar with copper. So copper expected would be argon. We have our 4s, 1, 2, 3, 4, 5, 3d, 1, 2, 3, 4p. So expected would be 2 4s and 1, 2, 3, 4, 5, 6, 7, 8, 9, 3d. Again, that's not stable. To pair up the 4s and to have that single unpaired electron in 3d, so what we see is argon. We see 4s, 1, 2, 3, 4, 5, 3d, 2, 3, 4p. What we see is a single 4s, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 3d. So the actual for copper is argon, 4s1, 3d10. Okay? Now, there are several other exceptions on the periodic table, including the lanthanides and the actinides. When we get down into those F electrons, there are a lot of exceptions. So I want you to know chromium and copper exceptions, okay? For anything else I ask you that could have an exception, what I'll phrase it as is, according to the periodic table, how would you expect this element to be filled, okay? If I'm asking you for one that is an exception that I haven't had you memorize. Most things, though, are going to fill like we expect. So if I say, what is the electron configuration of oxygen? Okay, you should be able to figure out the electron configuration of oxygen. If I say, what is the electron configuration of phosphorus? Okay, be able to figure out the electron configuration of phosphorus. But as far as the exceptions go, the only two exceptions I want you to memorize right now are chromium and copper. When you do 141, you'll start working even more with the transition metals and other elements, and so you'll have more of the exceptions that you'll have to get used to when you get to 141. But for this class, for 120, I'm only asking you to memorize chromium and copper exceptions.